My name is Tim Harris. I'm Director of Validation Services. We're going to kind of give you a summary of what's going on in real-time applications and then kind of drill down with one of the partners we've done a lot of work with, and that's Mitel. And Malcolm, you want to introduce yourself?
Sure, absolutely. So I'm a Director of U.S. Systems Engineering for Mitel. I've done a lot of work with VMware. I was part of a session that we did last year announcing virtualization of real-time application, which in our case was voice. And I'm going to be telling you a little bit about what's new in terms of what we've done since that announcement last year.
Great. So we'll go ahead. There's a disclaimer. Tell you a little bit about what we're going to talk about. So we'll start with kind of background on what's been going on with real-time applications in terms of virtualization for the last couple years. And then we'll start focusing on kind of the most interesting use cases for us, which is probably voice over IP. And then I'll drill down a little bit on something we've done with some desktop applications in terms of real-time space. And then I'll pass the baton to Malcolm to tell you a little bit more about kind of once we've proven out the core technology for using voice over IP on ESX, working with Mitel, what they're doing in terms of larger kind of solutions around that technology. So before I jump into real-time in particular, I'm going to give a little plug for the project that I drive at VMware, because I think it is relevant to people in this room. What we do is in validation services is assist our ISV partners to uptake technology associated with VMware, obviously, but particularly virtualizing applications that have never been virtualized before. So often we're talking to ISVs out there that for some reason either they tried it 3 years ago or someone told them it doesn't work, or sometimes it's just anecdotal stuff that someone told them in an elevator that, 5 years ago, oh, performance sucks when you virtualize things, don't try it. So we're taking those kind of harder nuts to crack in terms of ISVs that don't currently support VMware as a platform, and working with them. We have lab resources, we have engineering teams, and we basically throw resources at this to help them get comfortable with it. And how that applies to you guys, assuming most of you are probably customers, is that if you're walking around the data center doing kind of what we would consider the right thing, that is looking for the next application to virtualize, and you're saying, how about this one? You call up the ISV, they say, hey, don't virtualize on VMware, we don't trust that platform, then you guys should essentially tattle on those guys, help us know who that is, and we'll work with them in a positive way. We'll offer them free resources to support an effort to test that application and hopefully prove it works well. And our success ratio is very high. So here's the URL where you can go and report, here's the application I wanted to use. There's a little box if you want to say, they told me they don't do it because of A, B, and C, or you can just put the application in there. We'll actually follow up with the ISV. If you put your information, we'll follow up with you to let you know the status also. So real people will call that ISV and say, hey, can we work with you to think about supporting the VMware platform? So now moving on to the topic. So real-time applications are extremely latency sensitive. Now, all applications are somewhat latency sensitive, right? So it ends up being a little bit of a subjective call of what's a real-time application. But if you are narrowing down on kind of what real-time is versus non-real-time, we think of real-time as ones that essentially break when they get too much latency, right? And generally, in terms of my team, we try and separate them into hard real-time systems and soft real-time systems. Hard ones being high-risk applications. So if there's a little extra latency, something bad will go on, right? So pacemakers is a kind of facetious effort, as we're not actually virtualizing pacemakers, but you can see that having a 30-second delay in pacemaker execution would be a problem. Maybe more realistic financial trading systems. There are certainly vendors out there that are selling financial trading systems with the assumption that they're a great product because if they're 10 milliseconds faster than your competitor, and then you will make more money, and if you're 10 milliseconds slower, then you potentially will lose lots of money. So that's kind of a difficult space for us. Generally, we avoid things that cost millions of dollars if we delay things by a couple milliseconds. So that narrows us down to soft real-time systems. Probably telecom voice over IP is kind of the obvious one that we've been working with the most, and which you'll learn more about in this talk. The good news is it's kind of technically challenging and interesting, so we learn a lot about ESX when doing that. And also, it's not life or death risky. We want to make sure that call quality is good, and we'll be talking about that. But if there's a glitch in call quality, it's not going to hurt anyone physically, which is kind of comforting. So let's talk a little bit about kind of how we got here and what's the history of real-time applications on ESX. We've had customer demand for quite a while. It kind of started from virtualization first shops, people who are virtualizing essentially all applications saying, hey, what about that one? Why can't I do that one? We as an organization, that is VMware, has always been a little bit cautious about this. And even today, we're kind of like, try it first. And that's why a lot of this stuff comes to my lab, because we don't necessarily make blanket statements that all real-time will work like this. We don't necessarily have guaranteed SLAs. Certainly in ESX35 and before, we're particularly cautious. And in fact, generally said, don't do it unless you've shown it works well in the lab. One of the reasons for that is our schedule is not really designed for real-time applications, and I'd say maybe more generally that real-time and virtualization kind of have conflicting goals to some degree, right? So real-time is really about being sure that you have CPU available when you need it, which might be all the time potentially. Where virtualization, our goal is really to spread resources across a bunch of virtual machines, right? So one is combining resources in one place, saying there it is. The other one's spreading them thin across a lot of virtual machines. So they really have kind of inherent tension. So it's hard to design a virtualization system that also works for real time, though I think we've learned that we're getting pretty good at it kind of by coincidence, if that makes sense. So before we kind of jump into any detail, let's give a little bit of background so we're kind of on the same page in terms of virtualization performance. The things we know about virtualization performance, generally we expect a little bit more CPU in the virtualized case, right? So when I'm not talking about real-time apps, which again, I'm not a domain-specific guy in real-time, we do all sorts of business apps. Typically, we spend a lot of time talking about how much CPU it is, how do we do capacity management without additional CPU to make sure we get good performance. Here, we're actually talking about the other two bullets more in the sense of real-time stuff. There's a little bit of scheduling overhead, and in real-time, that's very significant. This is generally so extra cycles as you're allocating CPU resources, and those extra cycles actually go up as the size of a virtual machine grows. So an 8 vCPU VM is going to be a little less efficient. Think about a couple % less efficient than 4 vCPU VM, and similarly. Having said that, you don't necessarily want to run with the smallest VM all the time because then there can be additional management with a whole lot of small VMs. So there's always this kind of trade-off. Again, in typical enterprise applications that aren't real-time critical, that overhead is so small that maybe people don't care about it. Maybe you don't worry about 3% or something, so you just go with the big VM if that's what you feel like you need for your workload. But these things are particularly relevant for things like real-time apps. Networking layer, there's also a thin networking layer that you should be aware of. Again, things that in typical business apps don't matter that much, but in real-time apps they do. I'm going to talk a little bit more about the technology, but VMXNet is a paravirtualized network driver that we've been using since at least 3.5. So let's talk a little bit about different technology. I mentioned the word paravirtualization without really defining it. So binary translation, again, I'm not going to give a whole lot of depth on this because this has kind of been around for a while, but binary translation is our general approach to virtualization at VMware, right? So we run a standard version of the OS, we get to the execution of some command that is the system interaction, and we essentially overwrite that with binary translation of that information so that we're interacting with the hypervisor directly. Okay, we like it because it uses standard OS versions. You're not using some OS version that you've never tried before, and it performs well, right? Paravirtualization, we're not against it, though we would rather run with standard OSs as we do, but there are certain cases where we can use paravirtualization. That's essentially rewriting functionality so that it directly addresses the hypervisor, and we tend to do that around drivers, right? So they're kind of an add-on to an OS, so they're not really impacting your OS directly. Specifically, VMXNet is the one that I mentioned, and which will come up a fair bit today. Another one that you'll see in vSphere is a paravirtualized SCSI driver, so you can actually do IOs through a paravirtualized driver now. Now, paravirtualized SCSI driver, we've also played with it a lot in the lab. It's a little bit out of the context of most of this talk, but it's a pretty specialized use case where we see benefits from paravirtualized SCSI driver. So generally, something like VMXNet, I'd say use it everywhere. Paravirtualized SCSI driver, if you have tons of I/O, like 2,000 IOs per second or more, then you want to think about paravirtualized SCSI driver. Another thing that we should be clear on in terms of kind of VMware's general perspective is hardware assist. So was times when we were a little concerned about hardware assist because we weren't really seeing gains from it way back when, and some people still ask me about that. Generally, we are very supportive of hardware assist That is, if we can take any functionality that's in the hypervisor and software today, and we can work with our hardware vendors to build that into the chip, then we want to do that. And it's more efficient. It takes cycles away from the hypervisor, so it's a good thing. So we're always in favor. In fact, if eventually all the hypervisor functionality bleeds into chunks of hardware that you can buy easily, then that's probably the best solution. So that's kind of where we're moving in general. Traditionally, we certainly verify that the performance is better, and if it's not better, we don't enable it. So there were cases in history where that was the case, but that hasn't been true for a little while. So what are the things that kind of have been improved since 3.5 days that really helped enable real-time? Scheduling of CPU, we have much more efficient scheduling algorithms. There's also co-scheduling is a big topic. If you have multiple vCPUs in a VM, they all kind of have to be aligned before you start, and we've gotten a lot better at making that less of an overhead now. Networking, VMXNet 3, a little update to VMXNet that improves efficiency a fair bit, and the hardware assist that I'll talk more about, which is memory management-focused hardware assist. So there's two flavors of hardware assist out there in the market today. So VT has been around for quite a while, so you can probably assume that any chip you run on, as long as it's not 5 years old, will be VT enabled. So VT is essentially the exit from user space, then you get to some system level operation, which is going to need hypervisor intervention. At this point, the chip will actually identify that and say, okay, I need to essentially transition control to the hypervisor. This is the case where initially these chips that came out with VT were actually slower than binary translation, than our own software version of this, so we didn't enable it for a while. Now all chips are faster, and we use it everywhere. So AMD and Intel all have VT-type technology, and we use it by default everywhere. So just assume you're probably doing VT everywhere. If anyone ever says, let's disable VT, it's kind of a silly thing to do. I don't know of a useful use case where you'd want to disable it. Memory Management Assist is much newer. Again, it came out with Shanghai and Barcelona on the AMD side, and that was available in 3.5U2 for a little while. But most of it's kind of vSphere stuff, and that's Nehalem with the extended page tables. So what that does is, one of the software challenges of virtualization is, okay, we use, this word is overused everywhere, virtual memory, like normal guest OSs use virtual memory, right? But we're, in the case of virtualization, server virtualization, again, apologies for the overused terms, you're mapping the virtual address space of that guest OS onto a much bigger physical address space, which is the underlying host memory. Traditionally, we've done that with something called shadow page tables. And so shadow page tables are a reasonably complex mechanism for mapping those memories from the guest OS to the physical hosts, assuming the physical host generally has a fair bit more than the guest OS does. And so essentially we're replacing that reasonably complex calculations that you do to manage memory in a virtualized system. And extended page tables is the Intel brand name. Rapid Virtualization Index is the AMD name. They both have similar technology there. So let's kind of go back to discussion of voice over IP as one of the most interesting use cases for real-time applications and virtualization. So first thing is, what are the metrics? So traditionally, voice over IP uses a mean opinion score in telephony quality in general. Call quality in general uses a mean opinion score, the MOS score, where 5 is a great number, 4 is pretty good. Those are kind of the targets we're getting. Maybe 3.5 is about where we start seeing quality issues that a customer might be concerned about. 3.5 and below is probably where we don't want to go. I'd also point out that there's a fair bit of technology involved that we work with telephony partners in order to drive load of simulating a whole bunch of calls, and also to monitor things like MOS score. Now, some of this technology is kind of proprietary and expensive, so when we run in our lab, we tend to look for what's a kind of easier metric. So the metric that our colleagues at Mitel are focused on is worst-case packet latency. So we see packets, that is essentially a packet of moving from one telephone headset to another through an application, it happens to be the telework application in the Mitel case, as consistently averaging about 20 milliseconds point to point. And that average actually doesn't change that much, but the worst case does change. And what we've seen is if the worst case is above 100 milliseconds, then call quality is essentially unacceptable. If it's below 100 milliseconds, then it tends to be acceptable. So though MOS scores would be an ideal metric, we don't have the technology in our labs to test it. This is the kind of analogous metric that works well and correlates well with MOS scores. So what we started to learn in the lab when we started running this stuff was the number of exceptions, the number of packets which exceeds 100 milliseconds substantially is actually very small. But the deltas can change call quality a lot. So when we saw less than, so both of these are less than 1% of all packets, but if we saw 0.04% of all packets more than 20 milliseconds, then we started to see call quality be unacceptable, so below 3.5 in terms of MOS scores. If it was only 0.2% of all packets, then we saw call quality that was acceptable. So it really gets into almost a finite number of a few packets per, say, minute that really can impact call quality. So generally, 99% of the packets just work in small latency, but a few would be problems. So kind of backing up a little bit, 5400 series of Intel chips is pre-Nehalem. It's been out for a while. We started kind of testing with that to see, well, how do we do with the kind of historical hardware that's out there? These are 4 vCPU VMs, and we saw worst case latency of almost 2 seconds. So there's some packets that are just getting lost out there, essentially. And they eventually would get to their destination, so these aren't drop packets I'm talking about, but it would be well over our SLA. So our target there, I'm trying to figure out this later, was 100 milliseconds. We were seeing 18 times that for observations of the worst case latency for a given packet. We looked into the code. It looked like memory management was related to the problem. And of course, Nehalem and also AMD both have solutions towards a more efficient memory management mechanism that I mentioned before, EPT in the case of Nehalem chips. So we moved on to 5500 series of Intel chips, which is the Nehalem with EPT enabled. And we saw latencies of 73 milliseconds was the worst case latency that we're seeing in terms of packets out there. So under the SLA, substantially, huge change in performance as we enabled EPT. Something else that worked here was smaller VMs also work. So even with the 5400 series, if you're running very small VMs, I mentioned there is some scheduling overhead with the larger your VMs are. And if you run with uniprocessor VMs, you can actually get away with even the 5400 series. But uniprocessor VMs, again, a lot of VMs to manage. And in the case of Mitel applications, it's not particularly convenient. So not a very interesting solution. So generally, we're using Nehalem chips, VMXNet 3. Now let's look at what EPT had to do with this. Again, there's kind of two components to the Nehalems, right? They're just generally faster chips, and that's true whether you're on physical or virtual compared to previous versions. And then they also have the virtualization-specific functionality, EPT, which only applies in the virtual case. So if we break those two kind of components of Nehalem performance out, we see that with EPT, again, 73 milliseconds was the worst case latency of a packet. Without EPT, we're up again to 450 milliseconds, so substantially over the SLA. So we learned that EPT is very significant. Nehalem itself is a fast chip, but without the technology to move our memory management overhead into hardware, we still had trouble getting to the goals of the SLAs we wanted for voice quality here. So the other thing, so I should point out, all this was done with one VM on actually a 4 vCPU VM on an 8-core system. So not a particularly production use case. We also wanted to know what happens when you start loading this host with other VMs, because obviously that's kind of one of the value props of virtualization is how many VMs you can fit on a box. So what we did here was run VMs that were running different workloads. They're actually database-intensive workloads. So it was kind of a mix and match of getting better, different kind of utilization patterns from different VMs and adding load in those additional VMs. So we went from the kind of, where am I here? We went from the kind of 20% utilization that we were seeing. Okay, that's, I guess one VM was around 20%. That's an interesting typo. I think our spell checker changed utilization to hospitalization. But So as we were adding load, we went from kind of the 20 millisecond, roughly one VM running, and then we added VM load to get to up to 72% utilization. So we saw that actually, surprisingly enough, the worst case latency actually improved here. So it started out around 90 milliseconds was the worst case latency. As we added load, it actually improved. Now this is a pretty surprising result, and I would say, I don't recommend you take this to the bank that worst case latency will always get better as you add load. But it did seem consistent in our testing. We talked to the guys who wrote some of the code around this stuff, and they said that it's possible this would happen. Again, no one wants to bank your future on this behavior, but there's some activities that are kind of opportunistic. So when you're in the VM kernel, it may actually poll to see if there's networks ready to go out or to be received in a way that if it wasn't in the VM kernel, it would actually have to do a poll based on some time metric timing out. So since it happens to be doing this work, it says, oh yeah, here's a network packet, I'm going to, whatever it needs to get done, I'm going to receive it or send it, and therefore we actually get a little bit better latency, worst case latency, once you're kind of active in the system and have a more CPU load. I point out in the beginning, capacity management is a big part of virtualized systems, just like it is with physical systems. So this doesn't mean you should run things at 100% utilization. That's why we kind of petered out at what we think is kind of a typical use case of production environment. People get nervous in production environments that start to get above 70% utilization, as they should. It does start to kick up here if you get towards 95% or 100% utilization. It'll certainly start to kick up. But what we did learn is it doesn't get worse. That's probably what I'd say from this data, is it doesn't seem to get worse until you're a highly loaded system. So that's positive, and this is probably the way people will actually run these things in production. So reservation and shares is another kind of interesting topic related to this. So hopefully you guys are familiar. This is the way you can kind of pre-allocate resources such that they're not as likely to be kind of borrowed by your neighbor in a virtual machine. So if you set reservations, you essentially have that CPU and memory resources allocated to the VM. And we certainly saw gains from this. I don't quantify them in this slide deck, but we see performance gains from using them, and it's probably worth doing. And I think Malcolm has some specific recommendations around that. I'd say I work with ISV partners all the time. Generally, I'm pretty cautious about encouraging reservations and reservations for either CPU or memory, because it does make for one, we find that customers start to ignore the recommendations if they're too broad. Of course, every ISV thinks their application is the most important application, and so you end up with a bunch of ISV partners saying, no, you should make ours have a bigger reservation than another VM, and it ends up being a little bit challenging if you're setting up VMware HA. You probably know you need a little bit of extra capacity in case you lose a host and you need to be able to boot those VMs up on other hosts. So we're pretty cautious about setting reservations and shares in general, but in the case of voice over IP, which is obviously performance-centric, it's useful and probably worth doing in that case. So I'm going to kind of, so best practices, smaller is better. You can run small VMs if you can, but I think that sizing-wise, Malcolm has much more kind of developed ideas of what the size of the VMs are. MMU assist is critical. Again, generally we try and kind of get software vendors to recommend hardware rather than kind of require certain hardware. But I think in the case of voice over IP requiring MMU hardware assist for either Intel or AMD is probably worth doing. VMXNet is certainly the right way to go. The one kind of little bit of tweaking we needed to do is periodically you should definitely monitor drop packets in any network-intensive application. ESX top will give you that information pretty clearly. Once in a while, we need to set the number of receive buffers to something other than default. So the default is 256. If you see that one out of 1,000 packets gets dropped, you should increase that. And we increased it to 1,000 in some of this testing, or 1024, that is 1K. So once in a while, you need to do that. CPU memory reservations had a positive effect. Some stuff that's not on the slide. So we did try CPU affinity, that is pinning. We didn't see gains from that, which is, I think, kind of positive for me because pinning does disable vMotion, and so I would rather not encourage people to do it. There are some people who talk about, you have to do CPU pinning for voice over IP. We didn't see any real gain to that. Probably the one thing that we did see a gain for, which is a little bit more esoteric, is NIC pass-through. So you can use NIC pass-through and get a little bit less jitter, a little bit better worst-case latency. Again, in most technologies, it will disable vMotion also, and it doesn't look like we need it. So I wouldn't necessarily recommend it, but that's kind of if you really want to say, okay, I want to even have better latency, then consider NIC pass-through. There's a lot of technology right now, which I haven't played with that much, so I can't really talk it up too much, but technology out there today with things like UCS and other Cisco products, as well as other NIC vendors that will allow you to do NIC pass-through and still do vMotion through an emulation mode. So that's kind of what's coming today-ish. But again, I'm not really an expert on that technology, but you can walk around the floor and learn a lot about that. So if you really want to get artsy, that's probably as far as I would recommend going. So let me transition just for a couple slides to some other kind of real-time activity before we get more depth on what Mitel's up to here. So another space we've been looking at is real-time desktop applications, particularly financial desktop applications. So these are applications where typically the vendor will actually host in their data center a mechanism to spread a whole lot of financial information out there. The customers will then use in their desktop client and do a quick install of something that essentially sucks in all that data. And it's data in a lot of different forms. There's market news, there's live videos, there's stock quotes, there's portfolio updates. So a fair bit of kind of graphics as well as video in there. Again, we're kind of isolating out the trading component because we're really not trying to tackle that yet. A lot of these vendors, as I pointed out, really believe that that 10 milliseconds will risk $1 million for them. So we're probably not playing there. But most of these, the actual bigger install base of these applications is people like at VMware. We use some of these applications where our financial analysts just want to be informed all the time. So there's stock tickers buzzing by. There's graphs on stock prices and other market information, as well as live video about stuff. So typically, so here we're looking at desktop performance, right, with our View product, if that's not clear. One of the challenges we have with looking at desktop performance is it's a little bit harder to get quantitative metrics. So what I'm going to be talking to you about here is kind of subjective metrics. And that's because what you really want is rendering time, right? So most load driving mechanisms that we use in enterprise apps on the server side are basically simulate the client. And they'll tell you when, from the server side, we thought we had sent something out, or from the server side, we thought we had gotten a save command completed, whatever. But in this case, when you're focused on desktop performance, you're really trying to figure out when the bits get rendered on that screen. So there's some technology for this, but basically this is mostly subjective. In fact, when we work with ISV partners on this, they mostly say, okay, we'll fly out and look at it. So that's why we end up with a little bit more subjective metrics. The big changes here in what we've been doing for desktop virtualization is the protocol. So as you guys probably know, RDP has been around for a long time, and we've used it as our desktop protocol for a while. But in the last year or two, we introduced PC over IP, working with a partner, Teradici. So there's a software version of PC over IP and a hardware version of PC over IP, which this depends on having a client that has a Teradici chip inside of it. So there's kind of 3 flavors of protocol. And what we wanted to do is how does this type of application work with those 3 flavors? So this is a typical View setup that we're using. It happened to be Nehalem, again, Blades, and NetApp storage. This is the 2 different devices we happen to use, though there's a lot of these out there. It happened to be a Samsung device that had the hardware chip enabled, so it had a Teradici chip in there, and a Weiss chip Weiss terminal that was not hardware enabled. It happens to be View 401. So again, there's 401 out there. We have not gone back and retested this in the last couple months yet. And we used a WAN-M as a simulator for WAN latency. So we kind of tweaked WAN latency as to see how that affected the performance here. So quick summary of what we learned, probably the hardest thing. So text and graphics, that stuff's essentially easy for this system, and whether you're RDP or PC over IP, it just kind of works. So video is really the challenging use case here. So when we ran PC over IP with some simulated latency, we saw reasonable performance, but particularly as you full screen things, you would see some pixelation. So it's a reasonable solution, but if you really want the perfect graphics of HD style video that looks like a television, we saw that available in PC over IP with the hardware chips. So again, it looks like physical. There was no obvious cost of virtualization from the desktop perspective, and we were able to full screen video in HD stuff and see very little impact to virtualization. So again, you'll see that I didn't mention partner names in here. These guys are very sensitive in terms of when they're going to release products and how they're going to go to market with those products. But I think from our perspective, we've proven out the technology pretty well. I would, if again, as I mentioned earlier, if you want to use these products virtualized, ping the vendor. Hopefully they'll say, yeah, we're working with VMware, and they'll give you a timeline. Or maybe they'll just say, yeah, we'll support it for you today. So we kind of leave it up to the partners in terms of their kind of go-to-market strategy. So I won't be able to mention their names right now because they're very competitive in this space. But we feel like we're making good progress with this use case. So at that point, I'll pass the baton over to Malcolm to tell us more about kind of what they've done with this technology.
Thanks, Tim. Let me just start off quickly for the audience that's here. Familiarity in the voice over IP space? All right, not bad. Familiarity with, so would that be in terms of you utilizing that within your companies or in the industry? Okay. And familiarity, last question, familiarity with Mitel? Okay, so that gives me a little room to just give you a little bit of background about us first, seeing as not everybody's too terribly familiar with Mitel. As Tim pointed out a little bit earlier, we've been working with VMware for quite some time now. We made an announcement last year around successfully virtualizing a real-time application, that being call control, in the vSphere environment. So we've moved along quite a way since then. We've actually released that product, generally available back in May. And we made an announcement on Monday, actually, that we've gone and expanded beyond that and included all of our UC applications, which is the real business value around doing voice over IP, having those fully virtualized and available as vApps. That's important because one of the things that I want to talk about is not so much in terms of what we've done in virtualizing. That in itself was a pretty major step last year, but driving home the real business value in terms of what we can do within that virtualized environment, plugging into the vCenter management tools and being able to provide higher levels of availability through the combined solution of what we would normally do from a disaster recovery or business continuity perspective and coupling that into the VMware environment. So hopefully I'll be able to give you a little bit more information about those areas. So probably very familiar, but I'll just start off in terms of the reason why we did this. Obviously, voice was one of those last bastions where there was dedicated hardware associated with that. We typically came from an industry where everybody had dedicated hardware, some type of appliance device with dedicated network interfaces back to the public switch telephone network, et cetera. In short, it was a duplicated type of architecture. So we're able to go and move it into the VMware environment. How do we come about to be able to do that? We decoupled our call control, made it software-based. First step we did was to be able to make it run in any x86 type architecture, which was the springboard to allow us to be able to look at virtualization. As Tim pointed out earlier, one of the main reasons why we did this, not maybe necessarily because we're terribly forward-thinking, although we are in our space. A lot of cases, what ends up happening, our CEO will attest to this, our best customers take us to the places where we need to go. So we had a lot of our customers that were actually interacting back in with VMware, probably talking into Tim's group and saying, what about this voice over IP application that I have from Mitel? I've tested it. It seems to work. There's a few things that need to be tweaked. What can we do to get the vendor together with you to be able to solve those problems? So that was the synopsis, I guess, in terms of how we got started in working with VMware. Tim had a similar slide that was up a little bit earlier talking about MOS scores. I want to give a little bit more background information on this. He was referring to our teleworker application, which is applicable from people when they want to work remotely, basically take that proposition that you have in the office, take it with you on the road, whether you're working from home, a Starbucks, whatever, make sure you get that same quality of experience. In this particular case, we're highlighting the MOS score elements as well. You see that down at the bottom, but for those that are very familiar or knowledgeable in terms of what goes on within the voice over IP space, there's two key components. One is the call signaling, which is relatively minor in terms of the overall network and CPU load that goes on. The other is the media stream. So in a lot of cases, when you're just simply doing calls back and forth, depending on where those calls are going, those are just simply running across the local area network or maybe the wide area network. And so the media stream is really not being impacted through virtualization. Translation is there's not always a terrible amount of load associated with that. This particular slide is illustrating doing the call control element coupled with the onboard conferencing resources that are part of our application. So it's built right in. We have an offboard server for larger applications, but there's 64 channels that are available for conferencing on board. So the testing that we did here was based on what we would call average business grade use, 6 CCS, centum call second, if you want to know the actual definition of it. Really what that means is this is the type of traffic you would expect for an average business user. The rough translation is that user is going to have about 10 calls per hour. Right? Some people may say, I don't get 10 calls in a day. But this is the type of testing that we did, and in terms of the resources that you saw that were being utilized, the first point, as I mentioned earlier, we're compressing, or we're actually going through and using the conferencing resources. So the media stream is actually going through the virtualized machine in this case. So the loading that we're seeing is not kind of black magic around the signaling, but rather looking at the media stream associated with that as well. And we achieved the toll quality that Tim was referring to earlier. The other thing that happens sometimes as well when you look at the call control, there's compression that goes on in some cases as well. If you're going across the wide area network, you need to be able to go and convert that over, compress that so it takes a smaller footprint across the wide area network. That also is going to go and use resources on the virtual machine as well. So we've tested against that as well. In this particular case, the other element that we had is we loaded it with other business applications that were running as well. One of the big things that we took a look at is virtualization on its own has a lot of benefits in terms of deployment, in terms of business continuity, as I pointed out a little bit earlier. But the real driver is there's not a terrible amount of benefit to this if as an organization, supporting virtualization using vSphere, for example, if you cannot coexist your voice application with other business applications, whether that be Exchange, SAP, those sorts of things, you've significantly diminished the value of what virtualization can achieve for you. So one of the things we support fully at Mitel is the ability for application coexistence, Mitel and other applications. So in this particular example, the machine, we had 16 virtual processors that were there, roughly about 2.25 gigahertz apiece. We were utilizing 4 of those virtual CPUs, 6 gigahertz were reserved for that. We only used 17% of the resources, and we actually loaded it up to, you can see on the chart over here, once we got up above 80%, we started to see a performance drop-off. So a lot of these metrics, this is where we drove our metrics in terms of the resource allocations that we were looking for, and also a real live business case study in terms of what type of performance levels you're going to get real world with it. I mentioned a little bit earlier that what we had done at Mitel since last year is to go and take our unified communications applications and fully virtualize those as well. These are listed up here. They're all virtual appliances. So we're delivering those in the OVF format, so you're able to plug and play right into a vSphere environment, versus other architectures where people will go and take a physical-based application and say, well, you can go and run it virtualized. A little more cumbersome to be able to deploy it that way versus this way. Pointed out earlier, we did our call control at the top, software-based. We added our MAS, which is the Mitel Application Suite. That allows you to be able to do things like voicemail, unified messaging as a component of that. Conferencing and collaboration, so audio and web conferencing together. Obviously some big benefits associated with that for people that work remotely, trying to get people together via conferences, and remote workers. The resource allocations that we have are all listed across the side. I won't go through all of them, but as you go through, you'll see some require more in terms of disk space, CPUs, those sorts of things. If you take a look at, for instance, the application server, you see that it has a much more hard disk space. A couple of reasons for that. The audio conferencing server is going to do things like recording and storing the files on it, so it's going to need some more space associated with that. Also, voicemail typically is an intensive application in terms of disk usage and storage that goes on with that. We also have our Unified Communicator Advanced, or UCA 3.2 application, fully virtualized. It provides presence, availability, and soft phone type capabilities, and an overall UC, Unified Communications Desktop Client environment. And then finally, our MBG, which is a Mitel Border Gateway, which does things like network access traversal. It's session border control as well, and does our teleworker application. So our complete UC suite is now fully available as virtual appliances. Okay. I've got a couple of slides here, and in the interest of time, I'm going to assume the audience is fairly well educated in this background. I'll just quickly go through these, but really what I wanted to do is transition from that in terms of what we've done around enhancing the DR and business continuity, or disaster recovery and business continuity elements that are already inherent within vSphere. So as everybody knows from an encapsulation perspective, one of the key benefits is that whole file structure is available as a virtual machine, files on a disk type, and it simplifies a lot of things around provisioning and redeployment of those resources. When you take a look at various ways of being able to recover, there's a number of different methods that are utilized. So next slide, actually. You take a look at virtual machine backups, server-based, or as you go down this, each of these are faster methods that you can do for disaster recovery, all the way down to storage array-based replication. So these are elements that are part of virtualization in general, and then those are typically looked at from a non-automation process. Site Recovery Manager allows, as everybody in the group probably is very familiar with, allows to automate a number of those tasks that are there. And so this is sort of the jumping off point in terms of one of the differentiation points that Mitel has, another one actually, is in terms of being able to support the vCenter management tools as well. So this particular slide, well, it looks a little bit busy. It lists all of the management capabilities that are part of the vCenter or vSphere and vCenter suite. And you can see through that we've got pretty much across the board support for all of those within the Mitel Unified Communications and Call Control suites. The exception being, and normally I highlight this, is across the top on fault tolerance. Now, if you're familiar with fault tolerance, it requires a number of key things, and Tim was pointing out earlier some of the key elements that we looked at around being able to successfully virtualize a real-time application like call control were around things like multiple CPU support, hardware assist was another one that was in there, and paravirtualization, right? Any one of those, if you're not able to support those, would, in our case, would limit the availability of that application to be run in a fault-tolerant environment. In this case, we've listed here that fault tolerance doesn't support multiple CPUs. The reason why I'm pointing this out to you is while fault tolerance would maybe represent a holy grail of direction of where things could go in terms of being able to provide a high level of availability, spawning virtual machines automatically, failing over, et cetera, in this case, because of the requirements that we have, you cannot fully do that. So there's an advantage that we have in terms of our architecture and what we would traditionally do in a voice over IP perspective at Mitel around resiliency. So being able to have, and I've got a couple slides to explain it for those that aren't familiar with it, being able to have a virtual machine or actually have a call control element running and have a phone be able to talk to not only one instance but a secondary instance. Normally that's hardware based. There's a lot of cost associated with that. So I'll walk you through just very quickly in terms of the levels of availability that we have, ranging from 3 nines of availability, which is kind of an industry term you take a look at. Really, it's a longer discussion normally. You look at a whole bunch of things. You look at the hardware, you look at the application availability, you look at the network availability. All of these things combine together to give you anywhere from 3 to 5 nines of availability. If we look at a single VMCD, or Mitel Communication Director, our call control running, we get standard 3 nines of availability. That's enhanced over our regular application that we run through some of the elements that are part of vSphere around encapsulation and isolation for that application relative to the other apps that are running there. So in this particular case, you're going to have your phone. It's going to register into that single Mitel Communication Director instance. We can enhance this, moving it up to 4 nines, by adding the vCenter tools that I just mentioned a little bit earlier. So what that does is it allows us to start taking a look at things like vMotion, high availability, and Site Recovery Manager. And I'll stop and I'll point out very quickly, if my slides and that don't maybe capture exactly how this works, we've got a demonstration on the show floor. Our booth is 109 on the floor. Certainly drop right around and take a look, and we'll be happy to walk you through and show you at whatever pace is relevant for you. You see it working. In this particular case, what we can actually do is you'll see the phone still registered to that primary instance of the Mitel Communication Director. We're adding vMotion and high availability to this. So what will happen is in a detection of a VMCD failure, or maybe if you're going to move an instance, maybe there's some planned or unplanned maintenance and you want to move that instance, you can actually, the controller it'll restart the other application or another instance of it, and then the phone will rehome to that. Now, in this particular case, in the previous case, you wouldn't have that type of availability. In this particular case, you can do that and be able to have a secondary instance run no problem at all. If we look at improving that with a resiliency, what we can actually do is ensure that in that same type of situation, you can start up a secondary instance. Actually, this particular slide, we've got resiliency. So what I want to show here is virtually like the first instance, but with resiliency, we get 5 nines of availability, because if there's a failure, I'll walk through, it's dual home call control. So each phone has a primary and a secondary instance. So what it does is it'll actually have a heartbeat back between the instance and the secondary instance. If it loses that heartbeat, it'll automatically fail over to the other. So it allows, in a situation where there's disaster recovery or some sort of failure associated with that initial instance, it allows the call to continue. It also allows the phone to home to a secondary controller, which you'll see here, in the instance of it losing its primary. It will also fall back. So normally there's a demonstration that I do where we're actually having a phone call, and we go through and we show that, and we demonstrate that there's no interruption in the call that's going on, despite the fact that the primary call control mechanism has actually shut down. Okay, so in a failover and recovery scenario in this particular case, we can have an instance, we monitor, the VMCD fails. It'll automatically home to the secondary instance that's there. As I said, the call will continue on until such time as the primary is recovered. You know, that could be some form of automated recovery, or it could be a management assist recovery for it. That phone's going to rehome to it. Where this gets better or significantly improved in combining the two solutions together is if you look at using vCenter tools as well, and we start looking at high availability and vMotion, we actually have the ability to go, same idea again, you get your primary and your secondary. When we look at it resilient in combination with high availability, what will actually happen is the detect of the failure and restart, there's no deterioration or loss of service in this particular case. So on top of us being able to have a primary and a secondary failover point, we can actually continue to spawn instances. So we can have a third or a fourth or beyond from that perspective. So it significantly enhances the availability of the solution over what we were able to do with just plain plain resiliency before, on top of the economics associated with getting rid of redundant hardware that we had. Okay, so it's basically just showing the same operation before, but in this case you'll see the instance comes up on a secondary resource. And I believe that's it on that particular slide. So I want to just stop and see if we've got about 10 minutes left, see what questions you might have in terms of what we've gone through here for Tim and myself. Yes?
In a hardware situation, you would have something in front that routes, like you had that failover opportunity, you would route to that second hardware device in case the first one failed or something that.
Mm-hmm.
How does this change that scenario? You don't have to have that anymore?
There's not necessarily a requirement for a secondary piece of hardware, although it gets significantly improved if you've got a dual data center type architecture. But really what it's going to do is whether it's a physical environment or a virtual environment, it's going to have a primary IP address and a secondary IP address that it will look at. And in instances where it's recreating that IP address is going to be recreated in a different location, but it'll be the same physical address as it was before. Yes? I'm sorry, I'm going to move a little more closer. I couldn't.
Timer drifts.
Oh, timer of the guest.
Yeah, so we haven't had any issues with it in this use case. So he's talking about sometimes the guest OS timer will drift a little bit from what you would see in a physical system. We haven't had any issues with that. So we know it's a characteristic of virtualized systems. That Yeah, we haven't observed any problems with that. So. I can't hear you too well, Robert. Go ahead if you want to.
So with Linux, some of the older kernels in Linux, I think this timing and the clock, all those kind of things can cause problems with latency, etc. So Mitel standard Linux is for the operating system, which is all founded on Malcolm speak to that, but it's fair to say I believe it's based on current iteration of Linux kernel, and therefore the time is off. It's a tickless kernel. I wouldn't say it's tickless. I would say it's optimized.
Yeah, it's an optimized version, hardened version, basically, of Red Hat.
Uh-huh.
Can you tell me what percentage of your customers are virtualized or flash virtualized?
I don't know that I've got the exact percentage numbers, but what I can tell you is initial case. We've got a number of case studies that we've published already, a number of customers that have made the transition. And the interesting thing that has occurred is, in a lot of cases, the drivers for customers, on top of the usual capacity utilization thing, open a new location, whatever that drives them to move to the next level to add on capacity. The real interesting thing that's come up is customers who are looking, based on current drivers that we see today, real factors that have occurred around disasters, those sorts of things. Disaster recovery and business continuity are critical, especially if any loss of communication services can be detrimentally impactful to that business. They want to make sure that they're always going to have their voice communications available. And what we've seen is a lot of these organizations have already gone and virtualized other applications. They've got a data center that's there. They're running vSphere. And so that question comes up, why not voice? Or we might go and talk to them and say, why not voice? And so sometimes there's a little bit of caution associated with that, naturally. It's real time, it's critical, as they pointed out. But from a DR perspective, resiliency improves the availability that they have there. So those customers initially that are in a physical situation, what we've done and a lot of what they have done is deployed resiliency as part of their vSphere environment. So they've virtualized and they've made those users still physical today. But in the event of some type of planned or unplanned failure that's there, they flip over in the resilient environment. So it's a real easy way for them to get comfort with that. And what we've seen with most of them is once they've gone and done that test case scenario, they've actually eliminated the hardware or the physical-based entity for the Mitel call control. We call that a 3300. They've gotten rid of that. In some cases, those customers might not have been ready to go the full enchilada, moving towards SIP-based services for whatever reason. Maybe they've got locations that SIP isn't available in that particular location, or they're not quite comfortable with how SIP-based trunking works. What we're able to do is redeploy the Mitel hardware as a media gateway. So basically, it performs the PRI type functionality, the analog interfaces, those sorts of things, and then does an Ethernet connection back into the vSphere environment and communicates via SIP. Yes. Typically, no, although I will point out in our demonstration environment that we have down on the floor, there's a small, perceptible, the call stays up, but there is a break. In the demonstration that we do, we have music on hold. So we're demonstrating that constant media stream that's coming from the initial instance. We show you moving it over to the second. There is a bit of a break there. I think that's got more to do probably with we're not staying within our own parameters on our demo environment. But no, normally there wouldn't be any interrupt there at all. But the call does stay up. And I guess if you don't stay within the boundaries that we have for the engineering requirements with it, then you would see what we've got down on the floor, which is about a half a second type delay. Any other questions? Today, 1,000 endpoints, but we're going to rapidly scale that up. Next release, we're going to get that over 2,000. The other benefit in terms of the architecture is if you need to scale beyond that, you can just simply add additional virtual instances, right? So our architecture allows us to be able to go in a hardware-based sense, even though the hardware box on its own can't do 60,000 endpoints, we can scale or stack the physical environment to get us up over 65,000 endpoints. we can do a similar logical architecture in a virtual environment as well. Not with vMotion, but with fault tolerance. So there's some requirements that limit the effectiveness today of fault tolerance. Tim can probably talk to it a little greater than I can, but in a nutshell, there were 3 key areas that we required for us to be able to successfully virtualize call control. And so a couple of those are non-supported, a couple or more of those are non-supported today in fault tolerance. I can't speak to the roadmap elements, but that's going to continue to get better. And the expectation is that eventually fault tolerance will work in an environment like ours where we require a lot of resources, real-time applications. So right now, multiple virtual CPU support is not covered for fault tolerance.
So fault tolerance is one of our availability solutions, if you're not familiar with it. Currently, so it's essentially an active-passive mode where there's another VM doing exactly the same workload, and you can transition in real time if there's a failure. But currently, it only works with single-processor VMs, so 1 vCPU VMs, and that's a limitation in the current release.
Okay. Well, I think we're at the top of the hour. I thank everybody for their questions and coming and taking part in the session.